Now that we have a pretty solid foundation for stoichiometry, we're going to start to introduce a few variations and a few other things that we can come up with. I do want to point out that a lot of problems ask for things like the amount of reactant left unreacted, or the mass of a precipitate formed, or what is the actual yield of another thing. If we're doing these stoichiometry problems the way we have them set up, there's all the possible answers you'll need right there. So no matter what they ask, you have the answers. A lot of times it's just interpreting what the words mean. I set up these next two examples and they're a little different. I picked some things that may be more common. This C2H5OH is ethanol, which is grain alcohol. So when people talk about alcoholic beverages, that's what they're talking about, ethanol. They also put it in gasoline, like you'll see at the gas pump, may contain up to 10 or 15% ethanol or whatever. This is isopropanol, which is rubbing alcohol. And so what I want to look at here is, those are both liquids, and if we're going to do combustion of these liquids, which doesn't actually happen, it's the vapor, but we're going to start out with some volume, and then that adds another step, but not much of a step, all right? And in both of these cases, I set it up that way. In the end, I tossed in a volume of water collected, because that's something that would be pretty easy to measure, and that's the way we're going to set these up. In addition to our percent yield, we're also going to add in like an actual yield of the other product. So we can take our, in this case, 80 milliliters of water, and that's how much we actually got. So the question is, how much CO2 did we actually get? And we'll use our percent yield to get that. And there's other ways to do it, but that's kind of convenient. I set these up in advance to save as much time as possible. Then I just yammered on to lose that time. Let's take care of this right here, though. All right. Density is mass over volume. In this particular case, we have a volume and we have a density, so we can solve for mass equals volume times density. Our volume is 100 milliliters, and our density is 0.789 grams per milliliter. So we end up with 78.9 grams of C2H5OH. All right, so if you have a volume, you just use your density and get grams. Everything else is going to be the same as we saw it. So let's see if we can cruise through this. 78.9 grams. And we're going to divide by molar mass here momentarily. And 150 grams of oxygen. To turn grams into moles, we're going to need to divide by molar mass. I provided those to save us a little effort. So we will divide by the 46.08. and 32. Common question is like, does that 2 come into play versus the 3 we have there? The 3 gives you a ratio within the balanced chemical equation. That doesn't come into play for the molar mass. The formula is all that comes into play for the molar mass, and there's 2 oxygens in that formula, each at 16, which is why we end up with 32 there. All right, let's see what we get. Looks like 1.71 moles of our ethanol and 4.69 moles of oxygen. And you may recall from these previous videos, that is what we have, and I am militant about writing that word and the corresponding word, which is what we need. That gives us the basis for our stoichiometry. And over time, you can come up with some shortcuts or whatever, it doesn't matter. But for right now, every single stoichiometry problem is exactly the same, so all we need is one system to do them. And that system involves using the reactants compared to each other to find a limiting and excess. If we look at our balanced chemical equation, that's where everything after the first box comes from. It says there's 1 mole C2H5OH. And one of the ways that I cut corners is I know I'm going to need it down here as well. So while I have that number in my head, I'm going to write it right there. And then in the top, I need 3 moles of oxygen, 3 moles of oxygen. And that gives us, I'm going to put this in red, 5.13 moles of oxygen that we need, and 1.56 moles C2H5OH. That is our ethanol. All right. We have 1.7, we need 1.5. We've got more than we need. That makes this one the excess reactant, and we can label it as such. And we have 4.69, we need 5, we don't have enough. That makes this the limiting reactant. That's the one that determines how much product we can make in that later step. It's worth noting that when you're labeling your excess and limiting reactants, do it on the have side. This is the numbers you're working with because you have them. This is just the numbers that we're comparing to. We don't need those. All right, so that's our first step there. And our next step is to find some amount excess. And we're going to do that by taking what we have minus what we need. So for our amount excess, we're going to take what we have minus what we need of the excess, which is the ethanol. That's 1.71 moles of the ethanol. Sorry, it's a little cold down here this morning. And we're going to subtract the 1.56 moles. And that gives us 0.15 moles of ethanol excess. And that's our number in moles. We can get that number in grams by multiplying by our molar mass, our 46.08 grams per mole. And we end up with 6.9 grams of ethanol. In the big picture, you're going to see why it's useful to have these amount excess once we start doing solution stoichiometry. For now, though, it's just a handy way to keep track of mass so we can check things in the end. This is our excess. We want to get a theoretical yield. The theoretical yield is based on our limiting reactant. And again, if you're asked for a theoretical yield, but they don't specify which product, then you're going to find the theoretical yield for both products. In this case, we had 2 products, so that's what we're going to work with. Our limiting reactant, we had 4.69 moles of it. That's 4.69 moles of oxygen. And everything after the first box always comes from the balanced chemical equation. 3 moles of oxygen. And in this case, and I will try and do a little color coding here, I'm not very confident. 3 moles of oxygen for every 2 moles of CO2. Is that visible? Yeah. And that's going to give us 3.12 moles of CO2. And we can turn that into grams by multiplying by the molar mass, which is 44.01. And we end up with 137.5 grams of CO2. Oops. 137.5 grams of CO2. Our other product is the water, and we're going to use that for our percent yield in a minute. And our ratio is 3 moles of H2O. 4.69. We will multiply by our molar mass to turn that into grams, 18.02 grams per mole. Again, that's the molar mass of the water, 2 hydrogens plus 1 oxygen. And we'll end up with 84.5 grams, 84.5 grams of H2O. This is our theoretical yield. And then we move on to get a percent yield, and in fact I'm going to sneak in a slightly different order here. Let's check it while we have time. And I don't know what was a good color for checking, but let's check it. Our starting mass should be equal to the mass in the end. And the catch, as we had mentioned before, is in the end you have these products and you also have some stuff left over. So in this case you've got 78.9 grams and 150 grams, and that should equal our 137.5 grams plus 84.5 grams plus 6.9 grams. And in this particular case, it looks like that's 228.9, and we do end up with 228-ish over here, so that looks okay. It doesn't mean we did the problem correctly, but it means like our numbers add up, which is very reassuring. And after you're doing such a big problem, it's kind of nice to have some reassurance at some point. We'll get our percent yield here, and I guess we could be labeling things. This was our first step, this was our second step, this was our third step, this wasn't one of our steps, and we're going to do our fourth step. In the fourth step, we're supposed to calculate a percent yield. The equation's that your actual yield, which has to be given, divided by your theoretical yield times 100. In this case, the actual yield was 80 milliliters. So again, that's a volume. It is convenient that the density of water is around 1. That means that if we have density as mass over volume, our mass is going to be the density times the volume, and in this case, that's going to be 1.00 grams per milliliter times our 80 milliliters, which gives us 80 grams. So that's kind of convenient. Our actual yield, 80 grams of H2O, and I guess I put it as 80.0. And our theoretical yield was 84.5 grams of H2O. You'll notice that I always label this H2O so that I can match it to H2O, right? Because there's two products, and I don't want to accidentally put the 137.5 grams of CO2 down there. I need to compare H2O to H2O, what we did get of the H2O to what we should have gotten of the H2O. In this particular case, we end up with a 94.7% yield. And it's important to note that that applies to all products. They came from the same place with the same stuff in a set ratio, so in the end, the percent yield of one should be the percent yield of the other one. And I know we're getting a little tight on space, but I want to calculate our actual yield of the other product, because that's something someone might ask for. If you look at our percent yield equation, it's that the actual over the theoretical is going to get us percent. Well, we have percent now, and I'll use this kind of like a checklist. I have the percent yield, I have a theoretical yield, and I want to solve for the actual. And I'll rearrange that here so we can see it. Our actual yield should be our percent over 100 times the theoretical yield. And we have that theoretical yield right here, and actually right there. And we have a percent yield right here. And we're going to solve for the actual. In this case, that's going to be 0.947 times these numbers here. And since I'm a little short on space, I'm not super motivated to come up with both, we'll just say the 137.5 grams of CO2. And we end up with 130.2 grams of CO2. 130.2 grams of CO2 is our actual yield. We didn't explicitly ask for it up there, but we were able to find it. So once again, in slow-mo, we've got a limiting reactant and an excess reactant by comparing the reactants, and that's what we did here. All right? We've got the amount excess by subtraction of what we have, and we've got a theoretical yield by comparing the limiting reactant to the products. So those numbers are right there. And then we got a percent yield using the actual yield, that's right there. And then we turned that into an actual yield of the other product, which we weren't explicitly asked for, but there's no harm in doing it. I'm going to pause for a moment. Markers are situated to get this going. We're going to have this same setup. We have a slightly different density for isopropanol rubbing alcohol. And let's take care of that very quickly. Density as mass over volume. We're going to get our mass as our density times our volume, and that is 0.786 grams per milliliter, 508.9 milliliters, and that should give us 400 grams of isopropanol, C3H7OH. And that's the number we're going to start with down here. We've got 400 grams C3H7OH, and we've got 100 grams of oxygen. We're going to take those numbers and divide by molar mass to get moles. The molar masses I gave up there, 60.11. And we know 32. And this will give us what we have. We need that number to be in moles because the balanced chemical equation gives you a mole ratio, 2 to 9 to 6 to 8 in this case. These mole numbers are 6.65 moles of isopropanol and 3.125 moles of oxygen. I know my sig figs are a little jacked here, but sig figs are the least of my worries as I'm trying to keep track of numbers. These numbers were what we're given. That's what we have. Anything after the first box comes from the balanced chemical equation. Our balanced chemical equation tells us for every 2 moles of isopropanol. And again, just to save some time, you don't have to do this, but while I have that number in my head, 9 moles of oxygen, 9 moles of oxygen. So we're going to end up with what we need. Based on these starting amounts, how much of the other thing are we going to need? And in this particular case, we get 14.06 moles of oxygen and 0.694 moles of isopropanol. And it looks to me like we have 6.65 and we only need 0.6. This is by far our excess reactant. And 3 and we need 14. That's by far our limiting reactant. Okay? Something that's a little easier to spot over here as we're looking ahead at how to speed up these stoichiometry problems. I'm supposed to have 3 times as much oxygen as ethanol in this problem over here. It's a 3 to 1 ratio. So 3 moles for every 1 mole. So I can look down here and say, well, do I have 3 times as much? And 1.71 times 3 is 5.1-ish, and I only have 4.6. So in advance, we can predict that's the limiting reactant. And if you look at how stoichiometry is often taught, or people who've done stoichiometry quite a bit, they end up just looking at that ratio and making a prediction in advance, which allows you to skip that step entirely and just do one comparison. It's a little trickier when you have a 2 to 9 ratio here, but that's a 1 to 4.5, and do we have 4.5 times as much oxygen? Not even close. We have like twice as much oxygen. If you didn't like any of those words, you can ignore them all and just follow our process here, because that's what I'm going to do. We're going to calculate our amount excess. We'll do it in the same way. It's our have minus what we need. For our excess reactant, that's 6.65 moles of our isopropanol. And we'll subtract what we need, which is 0.694 moles. We end up in this case with 5.96 moles of that isopropanol excess. And we can turn that into a mass by multiplying by our molar mass. And our molar mass was 60.11 grams. And so we end up with around 358 grams of excess isopropanol. That is our excess. All right. Looking ahead, we need to get a theoretical yield. The theoretical yield is based on our limiting reactant, which is the oxygen, and blue. There we go. Our theoretical yield. We're going to compare that to our products, and that's the CO2 and the H2O. We've got 3.125 moles of oxygen. And we're going to need to make oxygen go away. The balanced chemical equation tells us 9 moles of oxygen. And now we want to find out about those products. And using our similar colors to what we had before, there's 6 moles of CO2. And so 3.15 times 6 over 9, we end up with 2.08 moles of CO2. And we can multiply that by our molar mass, which was 44.1 grams per mole. And we end up with, in this case, 91.7 grams of CO2. 91.7 grams CO2. There's our theoretical yield of the carbon dioxide. Our theoretical yield of the water we'll get by multiplying by 8 waters, 8 moles of H2O. 3 times 8 divided by 9 should end up pretty close to our 3 there, and it ends up 2.78 moles of water. We'll multiply by our molar mass, which is 18.02 grams per mole, and we end up with 50.1 grams of H2O. This right here is our theoretical yield. We can check things, and again, I'm going to declare that I'm going to start checking things now by adding up our mass. Our mass in the beginning should be equal to our mass in the end. Our initial mass is what we were given, which is 100 grams and 400 grams. And that should equal our excess, which was 358 grams plus 91.7 grams plus 50.1 grams. And we end up with, on this side, 141.8 plus 358, which gets us pretty darn close to our 500. So we will call that success. And then we'll get our actual yield and our percent yield and move on with our lives. Percent yield is supposed to be the actual over the theoretical times 100. We're given this actual yield of water, and again, I gave a volume, but we learned up here our mass is our density times our volume, and for water, 1.00 grams per milliliter approximately, times, in this case, 40 milliliters. So it's going to be 40 grams. And that's water, and I want to know that it's water so I can compare it to that 50.1 grams as our theoretical yield. This happens to end up 79.8% yield. And we will move on to get our actual yield of the other products. Again, setting this up in these steps, we compared our reactants to each other to find the limiting and excess. We subtracted to find our amount excess. We used just the limiting reactant compared to our products to find theoretical yield. We checked it, and now we've got our percent yield calculated using the actual yield that was given. And now I'm just going to sneak in this step of finding our actual yield of the other product. So again, we're going to rearrange this equation, and we're going to say that the actual yield is going to be our percent over 100 times our theoretical yield. And we have these numbers from previous calculations. The percent applies to everything, any product rather, because they came from the same place in a fixed ratio, so they got to have the same percent. So that number goes right there. Theoretical yield of the CO2, we could do either of those or both, and we multiply then 0.798, that's that number there, times our 91.7 grams, and we end up with 73.2 grams CO2 as our other actual yield. And again, you could take that 0.798 times the 2.08 and you would end up with 1.66 moles of CO2, or you could work backwards and divide this by molar mass and get 1.66 moles of CO2. So we've done a bunch of examples now of fairly straightforward stoichiometry, and we're going to work our way into other variations. Maybe problems that don't ask as much or sound different, or maybe they aren't given so explicitly. Because the reality is, in a textbook, they're not just going to say this. They might say something like, 100 milliliters of ethanol is reacted with 150 grams of oxygen. 80 milliliters of water is condensed after the reaction takes place. Find out your percent yield. And then all of this they didn't necessarily ask for, but in general you got to do it. And this is a really helpful step whether they ask for it or not, because it allows you to check everything. And to me that's a huge deal, because this is a bunch of work and it's nice to know that I did it correctly at that step there.